Hello everyone. In the previous lecture, we spoke about logarithmic mean temperature difference and we saw the equation for logarithmic mean temperature difference for parallel flow as well as for counter flow. In this lecture, we will talk about the another method of solving heat exchanger problems where we don't know the temperatures at the exit of the heat exchanger, or we know only two temperatures out of four temperatures. So if you know 3 or 4 temperatures, then we can go for LMTD method. But if you know only 2 temperature, or in a problem if only 2 temperatures are given, maybe generally at the inlet the temperature will be given and there will be no temperature given at the outlet. In those cases we have to go for NTU effectiveness method. So in this method, again the assumptions remain same as we had discussed in the LMTD method, and we need to arrive at an equation which satisfies Q equals U into A into delta T mean. So we'll start with this equation and then we will eliminate the temperature term from the equation so that we will be able to solve without knowing the temperature. Here I am considering the same tube-in-tube heat exchanger or the concentric tube heat exchanger which we had considered for the LMTD method. In this case, first I will derive it for parallel flow heat exchanger and then I'll give you the equation for counter flow heat exchanger, but the method remains same for both parallel flow as well as counter flow heat exchanger. So the initial steps remain same. I'll consider a small elemental area dA and I'll apply the first law of thermodynamics, which states that the heat given up by hot fluid should be equal to heat received by cold fluid, because one of our assumption is that there is no heat loss to the surrounding, so the heat transfer will be between the hot and the cold fluid. So I can write it as dQ will be equal to minus mHCpH into dTH, which is equal to mCCpC into dTc. So for hot fluid we have negative sign because the hot fluid is losing heat and cold fluid is gaining heat, so we have positive sign, and that can be written as that can be rearranged as dTH will be equal to minus dQ divided by mHCpH and dTc will be equal to dQ divided by mCCpC. Now I'll take the difference of dTH and dTc, so it can be written as dTH minus dTc will be equal to d of TH minus TC, which is equal to minus Q dQ into 1 divided by mHCpH plus 1 divided by mCCpC, and the dQ can be written as U into dA into TH minus TC. So I'll further simplify this. We have gone through the same steps in parallel flow heat exchangers, so I'll take the temperature term to the other side, so TH minus TC to the other side. So d of TH minus TC divided by TH minus TC will be equal to minus U into 1 divided by mHCpH plus 1 divided by mCCpC into dA. Now I'll integrate between the limits. As we know, for integration the limits are temperatures. For hot fluid at inlet it is TH1 and outlet TH2, cold fluid it is TC1 and at outlet TC2, and the area from the left it starts at 0 and goes to a maximum of capital A. So these are the limits which we need to apply. Again here we have a form 1 divided by x into dx. So when you integrate that you will get ln of x, and then you need to apply the limits, the upper limit minus the lower limit. So when we do that we get ln of TH2 minus TC2 divided by TH1 minus TC1, which is equal to minus U into A into 1 divided by mHCpH plus 1 divided by mCCpC. Now the product of mass into specific heat, that is mHCpH or mCCpC, we call it as heat capacity, and the heat capacity of one of the fluid will be maximum and the other fluid will be minimum. The maximum can be for hot fluid or it can be for cold fluid. So what I'll do is I'll write it as, instead of MHCPH and MCCPC, one of the thing I'll consider as minimum and the other thing I'll consider as maximum. So I'll write C minimum and C maximum in place of MHCPH and MCCPC. So here I have written C minimum in the place of MHCPH, but when solving problem, MCCPC can also be a minimum value. Now I'll take 1 divided by C minimum out of the bracket from this term. So I'll get minus U into A divided by C minimum into 1 plus C minimum divided by C maximum. And here I have ln, so I'll take it to the other side. So I'll get TH2 minus TC2 divided by TH1 minus TC1 is equal to e to the power of minus UA divided by C minimum into 1 plus C minimum by C maximum. I'll introduce a new term called effectiveness, denoted by the term epsilon, which is defined as Q actual divided by Q maximum. Q maximum is a new concept. Q actual is the actual amount of heat exchange that is taking place in the heat exchanger, but Q maximum is the maximum possible heat transfer that can occur, and that is given by C minimum into TH1 minus TC1. TH1 is the inlet temperature of hot fluid and TC1 is the inlet temperature of the cold fluid. So that is the maximum potential for heat transfer, and the amount of heat transfer also depends on the properties of the fluid. So here the product M in mass into specific heat plays an important role. Although one of the fluid will have a maximum value for that, so the amount of heat transfer depends on the minimum value. So Q max is given by C minimum into TH1 minus TC1, and that can be written as, so it can be written for hot fluid as well as for cold fluid. Here we have, this should be CC into TC2 minus TC1 divided by C minimum into TH1 minus TC1. So from this I can rearrange this, and I need expression for TC2 and TH2. So TH2 will be equal to TH1 minus epsilon into whatever we have in the denominator divided by CH. So that is TH1 minus epsilon into C minimum divided by CH into TH1 minus TC1. Similarly, TC2 will be equal to, so TC1 plus, because we have minus TC1 here, when it goes to the other side it becomes plus, or whatever we have in the denominator will be multiplied with the epsilon, that is epsilon into C minimum into TH1 minus TC1 divided by CC, that is the heat capacity of the cold fluid. Now substituting the value of TH2 and TC2 in the equation, TH2 minus TC2 divided by TH1 minus TC1 is equal to e to the power of minus UA divided by C minimum into 1 plus C minimum by C maximum. In this equation I substitute the value of TH2 and TC2. TH2 is TH1 minus epsilon into C minimum by CH into TH1 minus TC1. You can see it here, and TC2 is given by TC1 plus epsilon into C minimum into TH1 minus TC1 divided by CC, but here I have minus TC2, so here it will be minus TC1 minus epsilon into C minimum by CC into TH1 minus TC1, everything divided by TH1 minus TC1 into e to the power of minus UA divided by C minimum into 1 plus C minimum by C maximum. That remains as it is. Now I'll introduce one more term which I'll call it as NTU. The full form is number of transfer units, that is equal to UA divided by C minimum. So whatever I had here, UA divided by C minimum, I'll call it as NTU, or number of transfer unit. And what I'll do here is, in this equation I'll group TH1 minus TC1 together. So when I group these two together, I'll get TH1 minus TC1 minus, I'll take epsilon C minimum into TH1 minus TC1 as common, because that is present in both the terms here. So minus epsilon C minimum into TH1 minus TC1 multiplied by, since I have minus on both sides, inside it becomes plus 1 divided by CH. So here we have 1 divided by CH, and here we have 1 divided by CC. Now I need an expression for effectiveness, so I'll try to simplify this equation to get an equation for effectiveness. So you'll get 1 minus epsilon into C minimum. We don't have this temperature term, that gets cancelled here, because we have in all the three terms we have that, so here it gets cancelled, we don't have to write it here. So 1 minus epsilon into C minimum into 1 divided by CH plus 1 divided by CC will be equal to e to the power of minus NTU. NTU is UA divided by C minimum plus 1 into 1 plus C minimum by C maximum. As I said, I need equation for effectiveness, so I'll write the effectiveness equation as epsilon will be equal to 1 minus e to the power of NTU into 1 plus C minimum by C maximum divided by C minimum into 1 by CH plus 1 by CC. Now let us assume CH is greater than CC. The reverse of this can also be possible, CC can be greater than CH. For the simplicity, I am considering CH is greater than CC. So CC becomes C minimum and CH becomes C maximum. So the cold fluid has minimum heat capacity now, and the hot fluid has maximum heat capacity. So when I do that, I'll substitute that here in the denominator. So the numerator remains same, epsilon will be equal to 1 minus e to the power of minus NTU into 1 plus C minimum by C maximum divided by 1 plus C minimum by C maximum. So here I had 1 divided by CH plus 1 divided by CC. I have taken C minimum inside. So if C is C minimum or CH is C minimum, if I'll get 1 plus C minimum by C maximum. Okay, when this C minimum is taken inside, C minimum by C minimum will be equal to 1. In one of the case that happens. For the other case, it becomes C minimum by C maximum. Now if you look at C minimum by C maximum ratio, it is present in the numerator as well as in the denominator. In the numerator, it is present inside the exponential power, but in the denominator we have it added to 1. So what I'll do is, I'll define one more term called capacity ratio or heat capacity ratio, capital C, which is equal to C minimum by C maximum, because that is the ratio we have in the numerator as well as denominator. So I'm doing this because it will be easy for us to write the equation. So epsilon will be equal to 1 minus e to the power of minus NTU into 1 plus C divided by 1 plus C. So this is the effectiveness NTU equation for a parallel flow tube-in-tube heat exchanger. Again, if you look at a counter flow heat exchanger, again as we had discussed in the LMTD method, for a counter flow heat exchanger, the hot and cold fluid will be flowing in the opposite direction. That can be seen here in the diagram as well as in the temperature profile. So again here I will consider dA a small elemental area to find out the heat transfer, and then I'll integrate it over a larger area, and then I'll try to eliminate the temperature term with the help of the specific heat capacity of the hot and cold fluid. So when you do that, the final equation in this case for a counterflow heat exchanger, it will be epsilon will be equal to 1 minus e to the power of minus NTU into 1 minus C divided by 1 minus C into e to the power of minus NTU into 1 minus C, where C will be equal to the capacity ratio, that is C minimum by C maximum. When we go to solving the problem, we will see, based on the problem, we will decide whether to use LMTD or effectiveness NTU method. Thank you.